Hi there, and welcome to Telefunken. Today's video is one in a series on the vintage Roland CR-78 analog drum machine. In this episode, we'll be building a new logic board to replace one that suffered irreparable damage. This video will document the entire build process and show several key steps you can apply to your own builds. If this sounds interesting, stay tuned. Roland CR-78 was released in 1978 and featured 34 preset rhythm patterns and a series of 16 selectable preset fills. However, what really distinguished the CR-78 from the other drum machines available at the time was the ability for users to create or program and store their own patterns. Combined with the ability to keep time with an external clock, this made the CR-78 seem like a real musical instrument, and it was the first drum machine to gain widespread acceptance by professional musicians and featured on several contemporaneous recordings. The brains of the operation are housed on the so-called logic PCB and include the mask-ROM encoded NEC 8048 microprocessor that contains the operating system and factory preset patterns, and an outboard 2708 EEPROM and two SRAM chips that manage the task of storing and accessing the user patterns. The SRAM in the CR-78 are MUPD 5101C, a 1024-bit CMOS SRAM with 256 words of 4 bits each. Two SRAM chips provide the equivalent of 1 kilobyte of 8-bit RAM. CMOS static RAM requires the use of a small amount of power to maintain memory, 10 microamps that are drawn from the rechargeable battery soldered directly onto the logic board. The CR-78 was initially supplied with a 5.6-volt rechargeable 4N100AA battery, which was changed later in production to an only slightly more reliable 3.6-volt N-SB3 NiCad made by Sanyo. Sadly, these batteries have been the cause of the premature demise of many CR-78s. Over time, NiCad batteries can leak in an alkaline electrolyte that contains potassium hydroxide, which reacts with the carbon dioxide in air to form potassium carbonate, a white powdery substance. In addition, potassium hydroxide will react with and degrade the copper, tin, and lead in PCB traces and solder. This forms a non-conductive residue containing a mixture of copper oxide and copper carbonate on the PCB traces, and tin and lead oxides and carbonates on the solder joints. These corrosion products are not truly soluble in water, alcohol, or nonpolar organic solvents, and as such have to be removed mechanically or chemically using mild acids such as acetic acid, vinegar, or citric acid. I've determined that the CR-78 we have on the bench is too far gone to support a repair of the damaged logic PCB. This leaves us with three options to get the machine working. First, we could attempt to find a donor PCB from another CR-78. However, we know they're not exactly easy to find now, some 45 years after their release. We could attempt to reverse engineer the PCB and design a replacement and have the new PCB manufactured. Though not unachievable, this would have to be a true labor of love, as it's not a trivial undertaking to reverse engineer a double-sided PCB of this size and complexity. Fortunately, a third option exists due to the dedication of a Mr. Akira Honda, who's done all the hard work for us and designed and produced a replacement logic PCB for the CR-78. Mr. Honda is the proprietor of synthsrepair workshop located in Mexico City. He can be contacted via Facebook or via email at the address shown on your screen. Honda has produced a plug-and-play replacement logic PCB for the CR-78 that we'll use to get our machine up and running. To be clear, Honda has sold us an unpopulated PCB, so we'll have to populate the PCB before we can install it. Thankfully, Honda has provided some great documentation to help us out with our build. He's developed a 6-page guide detailing some of the choices you might have for populating the board. For example, the board is configured to use the original Atmel 2708 EEPROM, or by repositioning two jumpers, the board can use the more common and easy to find 2716 EEPROM. This configuration has the added advantage that by using the more modern 2716 EEPROM, the negative 5-volt rail in the power supply is no longer required. At the very least, this means your CR-78's power supply won't have to work as hard, but if you're converting the supply from one source voltage to another, it greatly simplifies the power supply design. Some of these issues are described in detail in our video on rebuilding the CR-78 power supply. Another useful tool that Honda provides is an interactive bill of materials. Honda provides a PDF listing of all the parts you'll need in order to populate the board, but in addition, he's also designed an interactive bill of materials that comes in handy when it comes time to break out your soldering iron. The interactive BOM has the ability to map parts according to their value or other designations. This makes it really easy to find all the 100K resistors, for example, and helps with a nice orderly build. To begin, we'll need to decide which parts we'll need to salvage from the old PCB. Other than the CPU, which contains the mask ROM encoded operating system, and the EEPROM, which contains the software needed to store user patterns, and the switches mounted on the PCB, there are no special proprietary components on the logic board. In fact, as we know we're planning to install the Tontec MIDI kit in this CR-78, which will take the place of the CPU, EEPROM, and RAM, we know we won't need to install any of these chips. As such, the only parts we'll be reusing in our build are those in the switch assembly. All other parts, including ICs, sockets, and Molex connectors, will be brand new. Before we get started, I wanted to say a few words of caution. In particular, I'd like to draw your attention to some errors in the service manual. The illustrations in the manual that show the voice board PCB layout and the power supply incorrectly label the power supply voltages on pins 23 to 28 of the PCB. Some of these mistakes are also present on the actual PCB itself, and some of these connections are powering the logic board. The service manual contains a list of errata on page 12 or page 34 of the PDF version that show the correct voltages. If you're doing any work on your CR-78, pay attention to this area and make sure you don't hook things up incorrectly, especially your new logic board. Double check that the connections on the logic board are correct before powering it up. The rest of this video will cover the actual build in considerable detail. In many sections, I've sped up the film by as much as tenfold, but this is still a very long video. Nor is this a small project, as what I've captured in this video alone represents more than 8 hours of time on the bench. You'll note that I've taken a very measured, stepwise approach to the build, one that may be too conservative for some, but you might also be interested to know that the board worked perfectly on installation without any need for troubleshooting or fault finding. I hope you find this video useful and that it can serve as an additional reference for anyone rebuilding their CR-78. Also, for your viewing pleasure, various sections of the video have a soundtrack consisting of sampled CR-78 presets and fills that I've cobbled together for your amusement. I hope you find them somewhat inspirational. This is nothing fancy, but just imagine what you can do with your own CR-78 and some talent. Let's get started. Well, we're about to get started populating the replacement logic board, and the way that I like to approach this is similar to how many other people approach it, and that is that I start with the lower components first. That is the components with the lower profile. So that might include resistors, diodes, and then I move up in terms of the geometry, the profile geometry. So I might then move on to things like IC sockets, transistors, capacitors, and then finally larger components such as switches and so on. So we'll start this build with diodes, and there are some 36 odd diodes. And if you've purchased this particular replacement logic board for your CR-78, you'll have the bill of materials that is provided by the vendor, and it shows the various diodes, all of which are the same type, 1N4148 or 1N914, and there are about 36 of these. I'm going to place them, and as I place them, I'm going to strike them off so that we know that we've populated all of the positions where diodes belong. And I'll show you how I go about doing that. So the diodes I've purchased are in a tape, and rather than trying to take off this tape one diode at a time, I'm just going to simply cut through all of these, since we have plenty of lead length here, and we don't really care about using something like lead length, for example, to denote polarity, because that's clearly denoted on the diode itself, unlike occasionally some other components such as capacitors and the like that use lead length to denote polarity. LEDs would be another example. Okay, now we need to bend these, and bend the leads rather, so that we can place them where they belong. And rather than utilizing an expensive or a purchased gauge for determining lead length, I'm just going to utilize my needle nose pliers. And I know that this is approximately the right position to hold the component in order to get the bends in the right position to insert it into this particular board. And this is one of the diode positions. This is diode 114, and you can see that by holding it at that particular position on the pliers and bending, I get a perfect bend in the leads and can install the component accordingly and repeat. Something I'm not sure I really mentioned is that before I get started on a project like this, I like to develop the bill of materials in such a way that it is going to be convenient to go through as I'm installing the parts, to make sure I can keep track of all the components that are installed as I go along. This board came with an electronic bill of materials, which is quite well developed, and I based mine on that one and then set about to put everything in order. So for example, all the resistors are in order of their value, starting with 10 ohms going up to 1 meg. And that allows me to go through my parts, which are sorted in order of value, and find them more easily as I go along. Similarly with capacitors, I've put them in order of their value. I've also indicated which ones are ceramic disc capacitors in orange here, film capacitors in blue, and electrolytics in red. I've also highlighted all of the components that we're going to be omitting from this build, because we're putting in an alternative CPU, so we won't be using a number of components such as the EEPROM and the RAM and a couple of the other chips. And as such, there is no need for all of these components, which are highlighted in yellow. And really, you can see there's quite a few. So I've designated those, and we'll proceed accordingly. So now on to the installation of the resistors, starting with the 10 ohm resistors. However, those are not required due to the fact that we're using the PIC-based CPU. So we'll go to the 100 ohm resistors. So as we know, the original CR-78 has a number of connections to the board, which are achieved with wire wrap methods. And wire wrap is a bit of a pain to attach and reattach. And given that what we're doing here is putting in a whole new board, and this may require some diagnosis if, for example, we need to troubleshoot whether or not it's working properly or not. We may need to attach and reattach the board. So a more convenient way of doing that would be to use terminals that facilitate attachment and reattachment. And these are examples. These are made by, I believe it's TE Connectivity. And these are little pins that insert in holes on the printed circuit board. And then these are little terminals, female terminals, that come down on top of the pin and make quite a firm attachment that is actually rated well above any power requirements that this instrument would be subject to. So I'm going to insert these pins into the holes in the PCB and then attach these little terminals onto the relevant wires, and that will be the new method of connecting the logic board to the rest of the instrument. I think we have about 24 or 25 of these things that we need to attach. Well, I'll do this one and provide you with an example of what it looks like. We can see that the solder flows through the pin and is actually making a good connection on both sides of the printed circuit board. So that's going to give us a really solid connection all the way around. Well, we have installed almost all of the parts onto the printed circuit board for the CR-78, and all but the trimmer potentiometers and the actual integrated circuits. But before we install the trimmer potentiometers, there's one more thing I would like to do to the board, and that is clean it. There's a tremendous amount of flux residue on the board. I'm going to use a flux remover, and that's something that I would not want to expose the trimmer potentiometers to because it could degrade the lubrication on the inside of the pot. So I'm going to clean the board first, then install the trimmers and clean up around where the trimmers have been soldered in and proceed accordingly. So this is one of the final steps prior to putting the board back into the CR-78. So we have the board clean, and the last thing we're going to do is put in these trimmer potentiometers, which we wanted to protect from the flux remover. The trimmers that we're using are these Born's 3296 series potentiometers. I don't know if you can really see that. 3296. These are multi-turn potentiometers, and this board is laid out such that these just pop right in, like so. And we'll just position the pot, bend a couple of the leads slightly. And again, this is one of the really nice things about the way this board is laid out, is that it has footprints which will accept this potentiometer as well as some of the other more traditional single-turn potentiometers. But I prefer to use these multi-turns. They really make calibration of these types of instruments a lot more straightforward than trying to do this with a single turn pot. These three are all 50K. As a final check of board integrity before we populate the sockets with the integrated circuits, we're going to go through each of the sockets and check for ground on each ground pin and make sure that the ground is not shorted with any of the power lines, so that we don't have any shorts when we power the board up. And the ground pin is generally the last pin on the first row of pins on an integrated circuit. Not always, so check your data sheets. And then the VCC, or the positive supply, is usually the very last pin. Again, not always, check your data sheets. So we'll be connecting to a ground pin here, and first checking for continuity on all of the grounds. We'll start up here, and of course the little divot denotes pin 1. So this would be our ground, ground, ground. Oh, and on these RAM chips, I believe it's pin 1, 2, 3, 4, 5, 6, 7, or 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have ground everywhere where we expect ground. Now do we have ground shorted to the positive rail on any of these? And that's exactly what we would expect. The answer to that is no. How about the +5 rail? Is that being supplied to all of the integrated circuits that should be getting +5? That's not +5. That would be a different rail on these RAM chips. So we have continuity of the positive rail everywhere where we expect. And nowhere where we don't expect it. And one thing. So do we expect +5 on the op amp? No, we do not. We would expect +15 on the op amp, and that's exactly what we see. I think we forgot to check the ground of the op amp. We have ground where we expect it and nowhere else. So all of that is good. -5, we don't expect to see that anywhere. The only place we would expect the -5 would be over here on the EEPROM, and we don't have it because we didn't install the components to supply the -5 rail. And so that's exactly what we expect. So far, no horror show surprises waiting for us that are likely to result in letting the magic smoke out. And that's what we're looking for here. So with that done, I believe I can go ahead and populate the integrated circuits and think about putting this board back into the CR-78. Well, that's all for this installment in our series of videos on the CR-78. In a future video, we'll revisit the subject of MIDI kits and install one as promised. We'll also be calibrating the instrument to make sure that it's working as well as it did the day it left the factory. I hope you enjoy this series as much as I did making it, and as always, your comments, feedback, suggestions, and questions are most welcome. Thanks for watching.